Hello all, welcome to part 9 of the Assembly Language Primer for Hacker video series. In this video, we will look at conditional branching instructions in assembly. The first family of instructions we will look at is the conditional jump family. Now the conditional jumps are of the form JXX, where the two X's could be replaced by various letters denoting various form of jumps. Examples are JA, which is jump if above, JE, which is jump if above and equal to, so on and so forth. Specifically, we would like to note the JZ and JNZ, which is jump if zero flag is set and jump if zero flag is not set. So exactly how do these conditional jumps work? Well, basically, whether a conditional jump is going to happen or not is dictated by the state of the various flags in the E flags register, namely the zero flag, the parity flag, the overflow flag, the sign flag, and the carry flag. So what happens is that while various instructions are executing in an assembly language program, the processor sets many of these flags appropriately based on the result of those operations. Now, a programmer could use these flags in order to infer what happened in the previous instruction and then go ahead and take a decision and go ahead and conditionally branch out or jump to a separate instruction. So conditional branching is very, very important in programming simply because this is what typically allows programs to take decisions based on various events which are happening. A point I'd like you to note is that conditional jumps only support the short and near jumps. Far jumps are not supported. Well, now let's quickly look at a code example to look at the conditional jump instructions. There are probably over a dozen conditional jump instructions available and might not be possible to cover everything in this video. What we shall do is we will pick up a single pair of conditional jumps, which is JZ and JNZ, and then demonstrate how conditional jumps can be used. It is left as an exercise to the user to look at other conditional jump statements which are available and try and code their own examples. So now let's look at some example code on understanding these instructions better. So I've created a very simple program called conditional branching.s, which is available for download from the same page. First we have the data section where we've mentioned three strings: hello world, zero flag set, and zero flag not set. Then in the main function, we very simply have a statement which moves the value 10 into EAX, and then the JZ instruction which checks if the zero flag has been set or not. If the zero flag is not set, then the execution continues to flag not set print. If it is set, then execution is branched to flag set print label, which is this one, where we go ahead and print the zero flag set string. Finally, in each one of these, in the end, it just jumps unconditionally to exit call, which is very simply to exit the program. Now we've discussed many of these functionalities of how to write, exit, etc. in previous videos. So hope you are able to follow this. If not, please revisit them. Finally, we have a print hello world routine, which we will discuss a bit later. So let's go ahead and assemble and link this program. Right, and let's execute it. And as we see, zero flag not set is printed out. Let's load the program into GDB to look at it in more detail. Let's list the file, source code, and let's go ahead and break at this point, line number 20. Let's run the program now. You notice the program has hit the breakpoint. Let's look at the registers. And if we notice the E flags register, which is what we are interested in, the 0 flag currently is not set. Right? If it was set, we would see the ZF initials in the E flags register. So now let's go ahead and run this next instruction by stepping. Let's look at the flags again. As we can notice, the 0 flag is not set because of the move instruction. Hence, the next instruction, which is jump on 0 flag being set to flag set print, will of course not change the control of the program. Instead, the program will just move on to the next instruction. So let's step, and if we notice, it's gone to the next instruction, which is at line number 24. Basically the flag not set print, right? And let's go ahead, continue, and we'll see that the 0 flag is not set gets printed and the program exits gracefully. Now let's actually quit GDB, go back to our source code and add something which will go ahead and set the 0 flag. So let's say one of the instructions which we will use increasingly while creating our exploits, etc., is the XOR instruction. So XOR EAX. Now what this actually does is nothing but takes a logical XOR of the EAX register with itself. Now from basic math 101, we know that the XOR operation, when applied on the same entity, is going to give a 0. And thus the 0 flag will be set. So let's go ahead, assemble this new piece of code. Let's link it and then let's execute it. So if you notice, now we get 0 flag was set printed. Let's see how this is working internally by loading up the program in GDB. Let's go ahead, set a breakpoint again for line number 20. Let's run the program. Notice the breakpoint has been hit. Once again, this is the move L10 into EAX instruction. Let's step through it. And if we look at the registers, as in the previous case, we notice the 0 flag is not set. Now let's look at the next instruction, which is the XOR instruction. Step through it. Look at the flags again, and now if you notice, the 0 flag has been set because the XOR EAX operation resulted in a 0. Thus, when the next statement JZ flag set print will be executed and control will be given to the instruction at the flag set print label. Let's step through it, and what we will notice now is that from line number 22 we have gone to line number 35. Let's list the code around 35, and we notice that this is nothing but the flag set print instruction set. So let's continue, and the 0 flag was set is executed. So very simple program in which you use the JZ conditional jump in order to branch out based on various happenings in the previous instructions. I would encourage you to try out the JZ, the JMZ, as well as other jump instructions, and I'll leave it as an exercise to you to look at exactly how you can write programs using these instructions. Let's now go back to the presentation and to the next slide. So the next instruction for conditional branching is the loop instruction. Now this is very interesting simply because the loop instruction allows us to conduct or actually execute a set of instructions for a predetermined number of times. So let's say you wanted to print the hello world instruction, a hello world string 10 times. The way to do it with the loop instruction is load the value 10 into the ECX register. Now, the loop instruction is strongly coupled with the ECX register. In the sense, the loop instruction automatically decrements the value of ECX after completing every individual loop. Now, because of this, the number of times we want that set of instructions to be executed is stored within ECX. So a sample usage could be that you load the number 10 into the ECX register, and this is actually the number of times you want to loop the instructions. Then you go ahead, add a label at the beginning of the instruction through which you want to loop, and then go ahead, write that set of instructions which you want to loop over and over again, and then finally call the loop instruction, giving it the label of the starting point of that entire instruction set. So it's very simple. Let's go back and look at the code as to how we can do it. So let's scroll down now and let's look at the print hello world label. So if you notice, the first thing we've done is move the value 10 into the ECX register. This is the number of times we want to go ahead and print the hello world instruction. Then we have a label which says print 10 times, after which we have the push L ECX instruction. This pushes the current value of ECX onto the stack. And then this, as you can easily recognize, is nothing but the write instruction for the hello world string, right? After this, we go ahead and pop the value on the stack back to ECX. Now, I think you guys are pretty familiar with this part where we actually write hello world onto std out. But you must be wondering, why is the push and the pop instruction here? Now, if you closely look at the write instruction, when you call the write syscall, the address of the hello world string needs to be loaded into ECX. Now the loop instruction looks at the ECX register and then decrements it and continues the loop. Now we originally loaded the value 10 onto ECX. However, when write is being executed, this value is going to be overwritten by the address of hello world string. Now this is really not acceptable, because in this case your entire program will just go haywire and probably you will be looping indefinitely. So in order to not fall into that trap, what we need to do is save the value of ECX before we use the ECX register for any other purpose. Once that purpose is over, we go ahead and restore the original value of ECX, right? So this very simple piece of code illustrates the loop instruction. After popping the value of ECX back from the stack, we go ahead, use the loop instruction and giving it the starting point of the label, which is print 10 times, right? Finally, after 10 times the hello world string has been printed, we go ahead and exit the program by jumping unconditionally into the exit call label. Okay, so now let's look at the print hello world and see how we can print this. Let's go up here and let's go ahead and change this to print hello world. So now what will happen is XOR instruction leads to a 0, flag being set. JZ is true, because of which print hello world is called. Print hello world goes ahead and prints the hello world string 10 times onto std out. Let's assemble the program. Let's link it and then run it. And if you notice, the hello world string has been printed 10 times. So very simple program demonstrating how the loop instruction can be used. Once again, the point to remember about loop is that the value of ECX dictates how many times the loop instruction will run. At the very same time, if within the loop you're using ECX for any other purpose, remember to save it onto the stack before the loop begins and then retrieve it from the stack after every loop ends. Let's go back to our presentation. There are conditional loops also available, such as loop Z and loop NZ, which actually are also associated with the zero flag. So I'll leave this as an exercise to the reader to figure out how to go about using the conditional loop statements. So well, that's all for this video. Hope you enjoyed it. I would really appreciate if you could leave behind a couple of comments in the comment section below. Thank you very much for all the encouragement I've seen in the previous comments. Hopefully this is being useful and beneficial to you, and I'm very happy if it is so. Well, that's all for this video. Thank you.